Okay, we're going to continue on here a week ago. So I think we were talking about reactions and ways to classify reactions. And last time we really talked about one sort of big classification of reactions, which is double displacement reactions. And remember, when you have a double displacement reaction, that's sort of a big category of reactions. And it's always going to occur when you have really two ionic compounds. So you should always have two ionic compounds. And as soon as you see that, you should know it's a double displacement. And also, you should know that pretty much what's going to happen is we're just going to really swap partners here. So the two positive guys will switch partners. It will result in two new ionic compounds being made on the other side. And really, there's sort of two endings for this type of reaction in most cases, and that is two more specific classifications. One way is one of these guys may make a solid or a precipitate, which can be more specifically classified as a precipitation reaction. And a precipitation reaction, again, is a specific classification of a double displacement reaction in which a solid is formed. The other sort of common ending here for this type of reaction is instead of perhaps a solid being formed, you actually will make a water in this case. So water is another sort of outcome. And typically water usually will result from more specific classification of acid-base reactions that occur. And really the formation of a solid and the formation of water are two of the three reasons why pretty much all reactions take place is either you made a solid, you made water, or what we're going to talk about here right now, which is the other big classification of reactions, which is an oxidation reduction classification, or known as a redox reactions. And those reactions take care of basically a transfer of electrons, and that is really the third reason why a reaction takes place. So the two sort of big umbrellas of classifications is double displacement and redox reactions. And again, underneath those classifications, you can more specifically classify reaction in other ways. So let's talk a little bit about redox reactions here. Redox reactions are oxidation and reduction reactions. They always occur together. So if somebody's being oxidized, somebody's being reduced, and vice versa. So oxidation has several definitions, but the one mostly we use in sort of general chemistry is that it is somebody will lose some electrons. So if somebody loses electrons, that is oxidation. There is a definition of hydrogen and oxygen, which you sometimes will see in organic chemistry most of the time, but here we'll just focus on the electron aspect of it. Reduction means that somebody has gained electrons, and sometimes people remember this as Leo the lion goes grr, and that is loss of electrons, oxidation, gaining of electrons, reduction. Our people are fond of the oil rig as well. Oxidizing is losing, reducing is gaining. You can put Leo the lion on the oil rig and he goes grr. You don't have to choose. You can just remember all of them together. But that is a way that you can remember sort of what's going on. So what does that mean? What happens when somebody goes through oxidation and somebody goes through reduction is essentially their, really what it's called is their oxidation state, our number, changes. And you kind of think of it as a charge, but it's not exactly a charge. But you can kind of think of like the oxidation state on the left-hand side of the arrow to the right-hand side of the arrow. It will actually change. Now, when somebody loses electrons, they do become more positive, and that's because they now have more protons than electrons in that case. And when somebody gains electrons, they become more negative. So a very simple way to figure out what is being oxidized and what is being reduced is you could just think about it like a number line. There's like 0, and there's usually positive numbers to the right, negative numbers to the left. So if somebody is going through oxidation, what you will see if you look at their oxidation state or their charge on the left-hand side to the right-hand side of the arrow, you will see that it will be moving in this direction, in the positive direction, and that thing is going through oxidation. Now, again, if somebody's going through reduction, as you compare sort of their oxidation state on the left-hand side to the right-hand side, they will become more negative and move in this direction, and they would be going through reduction uh, in that particular process. One of the nice things about redox reactions is all you have to do is figure out one for sure, and then the opposite thing's happening to the other guy. So they always happen together. So if you're really confident like this guy's being oxidized, then by default, the other guy over there is going to be reduced. So they always happen together, and you actually just need to figure out one of them. So for example, if we looked at, something like sodium plus some chlorine here, making a little sodium chloride, and do a little balancing like we're in chemistry class here. There we go. Now, we could look at what's really their oxidation states, but we'll kind of think of it as charges if you want. Now, when we have an element on the left-hand side of there, sodium, that is an element that is uncombined, and any element that's by itself, how it naturally comes, not attached to anything, does not have an oxidation state. It's an oxidation state really of 0, really no charge. So on the left-hand side here, our sodium really has an oxidation state of 0. Chlorine, that is naturally how chlorine comes as a diatomic molecule, so it's not really attached to anything. It is a 0. Remember, things really only kind of get charges, for example, when they kind of hook up over here in our ionic compound, and the sodium on the right-hand side is +1, and the chloride here is actually -1. So if we wanted to kind of figure out in this particular case what is being oxidized, what is being reduced, once again, we could go to just a basic kind of number line approach. And if we look at the sodium on the left-hand side, it started at 0. And on the right-hand side, the sodium ended at +1. It is moving in the positive direction, which means the sodium here is going through oxidation. By default, that would mean that the chlorine here is actually going through reduction. We could also do the same thing for the chlorine. If we look at the chlorine on the left-hand side there, it's starting at 0, and it's ending on the right-hand side at -1. It's moving in the negative direction, and again, that tells you that chlorine is being reduced. So you could do it for either one, and you could use this kind of simple number line. And essentially what is happening here is the sodium is throwing some electrons over to the chlorine in this case. That is a transfer of electrons. That is a redox reaction. And that is the third reason why a reaction takes place, is basically that is what is taking place in that case. By the way, when we look at these two things, on the left-hand side, we have a metal and a non-metal. Based on what we've talked about before, we should always know that the metal should lose electrons, which means it should always be the one being oxidized. The non-metal in this case should always be the one gaining electrons, so it should be a reduction. So if you're comparing a metal and a non-metal together in a reaction like this, you should always know oxidation should occur at the metal, reduction should occur at the non-metal. But you could also use this, for example, if you're comparing two metals on each side. So if you're looking at, something like this to this. So take a moment and decide, is it going through oxidation or reduction here? It is going to be reduction here. If we look at iron on the left, it's +3, obviously. And obviously this guy is +2. So if we just go to number line, +3 is about here. And it ends on the right at +2, which means it is moving in the negative direction. And this guy is actually going through reduction in this particular case. So again, it's a very simple way to sort of figure out, as long as you're confident of what the oxidation state or the charge is on both sides of the elements. And we do this, by the way, usually for kind of element to element. So the same element on each side is what you should be comparing to see what is going on. Any questions on that there? And that is obviously what we just talked about there. Again, we're ultimately getting a transfer of electrons from the sodium to the chlorine. That totally missed in that case. All right. So again, as I mentioned, this is a redox reaction. It can also be classified as a simpler reaction as well. If we look at this one here, once again, magnesium on the left has no oxidation state or zero. And again, because it's not combined, our oxygen there also, that is naturally the way oxygen comes, which means it has a zero. But when that magnesium oxygen come together, like when I burnt the magnesium ribbon, I think that her week, and made that magnesium oxide, that is when the magnesium will get a +2 and our oxygen here will get a -2. So once again, if you were not sure, you could go to your number line and figure out what is going on. So magnesium is starting at 0 and ending at +2. It's becoming more positive. So as we would expect here, it is going through oxidation. By default, once again, that would mean that the oxygen here is going through reduction. And we can look at the oxygen. Oxygen is starting at 0 and ending at -2, going in the negative direction. And again, that tells you it's going through reduction. This is also a redox reaction that is happening. Again, ultimately what's happening here is our magnesium is sending some electrons over to our oxygen in this particular case. Any questions on that one there? Yeah. Yeah, redox is kind of like the shorthand name for oxidation reduction. It's a little less wordy than both names together, but it's the same thing. Yeah. Other questions? So again, these redox reactions are a big classification, as we'll see very shortly here. There is more specific ways you could classify these reactions depending on what's going on. You could also, sometimes we'll see the reactions written as half reactions, and they are half reactions indicating what is losing electrons and what is gaining electrons. So as we saw here, our magnesium went from 0 to +2. It's losing electrons. So this is our oxidation half reaction. And basically, we know it's the oxidation half reaction because our electrons are on our product side. So if our electrons are on the product side, then it definitely is an oxidation half reaction, like those electrons are being given off and released. This is our reduction half reaction here. And what we see is in our reduction half reaction, our electrons are on our reactant side, like they are being gained. They are called half reactions because, frankly, if you add both of those reactions together, the electrons will cancel and you'll get the overall reaction that's happening. Everybody on the left stays on the left, everybody on the right stays on the right, and you'll get the overall reaction. So if you see a half reaction that has electrons in it and you see electrons on the product side, that should indicate that it's an oxidation and those guys are being lost. And again, if you see a half reaction there and electrons are on the reactant side, then it is a reduction reaction, like they are being gained. Now you may be wondering, why is it 4 electrons? Each magnesium goes from magnesium to magnesium with a +2 charge. That is 2 electrons lost, and there's 2 magnesiums, which gives you 4 electrons total. Those electrons, again, are going to end up into our oxygen there. Each oxygen will end up as a -2 charge, right? So they gain the 2 electrons from each of the magnesiums in that particular case. All right. We're not going to worry too much about this, but there are 2 other definitions of oxidation and reduction that involves hydrogen and oxygen, just to put it down, but we probably won't come across it too much in here. Like I said, if you get to organic chemistry, sometimes you do come across it because there's a lot less, there are pretty much a lot of nonmetals involved. So oxidation can also mean that if you gain oxygen as you go from reactants to products, or lose hydrogen as you go from reactants to products. So that's an example of oxidation. Reduction, other 2 definitions are the opposite of that. When you lose oxygen as you go from reactants to products, or gain hydrogen as you go from reactants to products. So if you look here, We can see the sulfur has 2 oxygens. Over here, the sulfur now has 3 oxygens. So from left to right, the sulfur actually gained oxygen. So it's going through oxidation, the sulfur. Actually, it's the sulfur. The oxygen here is actually the thing going through reduction in this case. So sometimes, as you can see, there's no metals and stuff like that. So sometimes just looking at either gaining or losing oxygen or hydrogen is another way that you could look at oxidation and reduction. But for us, for the most part in this class and probably your other 2 classes that you may take, 1A or 1B, usually it's the sort of electron definition that you come across the most. And then when you get to organic, you kind of come across these definitions here. So not too much for those definitions to worry about for our class or probably your next couple either. So as we've been talking about, there's those 3 reasons why a reaction takes place. And as we saw last time a little bit today, double displacement reactions basically take care of those first 2 reasons, water being formed and solid being formed. And obviously, as we've been talking about here a second ago, redox reactions covers the transfer of electrons. And again, pretty much all reactions will boil down to one of these 3 things happening. So as we saw before, a more specific classification of a double displacement reaction, which is what this is a precipitation reaction. I know this is a double displacement, plus minus. Again, we just switch partners on the other side. By the way, just to be clear, in a double displacement reaction, there is no transfer of electrons. The charges don't change on things. Everybody remains the same charge from left to right, so there is no transferring of electrons happening. What I mean by that here, for example, that potassium is K+, that potassium is K+, this, bless you, that barium is +2, that barium is +2. So nothing really changes. That nitrate's -1, that nitrate's -1. That chromate is -2 and -2 on both sides. So nothing really changes in this case other than the sort of ion swap partners. There is no change in electrons and no change in what's known as the oxidation state in a double displacement reaction.
So for double displacement, how come we're going based off the charges, but like at redox on the reactant side, they're all zeros?
They won't always be all zeros on the other side. They are zeros because what we started with was just the element by itself, like in the sodium metal, just like this guy, right? That was just sodium metal. It's not combined with anything. So anything, remember, from the periodic table that if it is uncombined by itself, really has no charge and really is 0 oxidation state. So here when we're starting, say, with this guy, right, this K2CrO4, that's already an ionic compound, which means that they already have charges, right? So that's really made up of these 2 guys, right, and this guy, right? So we're starting with already in this reaction things that have already kind of run past that point, right? Lost electrons are charged, and now there's those ions attraction that's coming together, and that's what we're starting with here. But in those kind of redox reactions, you can have something on the left-hand side that does have like an oxidation state or, a charge or something like that. It just happens in those 2, we don't. And we know that, if it's something by itself, uncombined, it will be 0 and stuff like that. Yeah. Yep. So again here, this is a precipitation reaction, which again is classified as a double displacement reaction. And that is the only reaction, again, as we talked about earlier, that you will always start with 2 ionic compounds. So as soon as you see 2 ionic compounds, there's no other reaction that will do that. And they will always just switch partners. It's also important to remember that if you have to, for example, figure out what's on the product side here, we want to just think about the basic units of these guys like we talked about last time, and we want to put them together like we're doing nomenclature first. So that's potassium nitrate. That is why we do get KNO3 as the proper formula, +1, -1. We just need 1 of each. And these guys is +2 and -2, which gives us this formula. Then you want to balance. So again, sometimes people, if they have to like predict what's on this side, they will try to do the balancing and the formulas at the same time. So as we talked about last time as well, you want to always just start with the correct formulas, the basic formulas, like you're doing nomenclature or naming and putting things together properly. then you should go back and change the coefficients to balance it. Again, I can't tell you, how many people would write for potassium nitrate this, because they want to keep the 2's, and this is, again, incorrect. Yeah, so you want to make sure you first put it together correctly and then go back and balance it in that order. This is the other type of double displacement reaction I think we might have talked about last time, and this again falls under that double displacement umbrella. This is an acid-base reaction, plus minus, plus minus. Once again, we're switching partners. So 2 H's and an O make water, and K plus and Cl minus makes our potassium chloride. When we take a strong acid like this and our strong base, a reminder that we get 2 things. We get water and a salt, right? And the salt is just an ionic compound. And in this case, that is our ionic compound there, our potassium chloride. Remember that the ultimate reaction for this reaction, like we talked about when we did our net ionic equation, is the H plus the OH minus. So the H plus from the acid, the OH minus from the base, come together to make water. Again, that it will hit the net ionic equation for any combination of strong acid and strong base you put together. That is ultimately what you get when you get rid of all your spectator ions. And that, again, is the second reason why a reaction takes place here. We're forming water is ultimately what is happening here. And again, that is your net ionic equation. All right, so now we're going to talk about some redox reactions happening here. So again, these guys fall under the redox umbrella, our transfer of electron. Another example here, this is lithium, so by itself has no charge. That is naturally how fluorine comes. Again, really no oxidation state or 0. When those two get together, now we have an ionic compound, and now they will have a charge, so +1, -1. Once again, you could use the little number line if you like. We got our lithium starting at 0 and ending at +1. So our lithium is becoming more positive. Again, it is the metal, so we would expect that to go through oxidation. Here, our fluorine is starting at 0 and ending at -1. Once again, becoming more negative and is going through reduction. And again, in this case, it is our transfer of electrons that is happening in a redox reaction that's occurring. Now, a more specific classification of a redox reaction is one that we see here. This is what is known as a single replacement reaction on the bottom. And in a single replacement reaction, which is a more specific classification, you have A plus B, C. So you have just one ionic compound, and this guy could be a metal, and it will have really no charge at that point. Because it's a metal, when it does become a charge, it will make a positive charge. So it will come in and kick out the positive guy there. And the reaction you will get is this guy will then have a charge and make a new ionic compound. And that guy it got kicked out will come out with no charge. You may also remember this reaction as the one we did when we did that experiment where we had all those halogens and the different layers and the changing of the top layer color to the bottom layer color. When we did that experiment, we had like the heptane layer or hexane layer. And in that case, we actually had a nonmetal, and it would come in and kick out the negative guy in this case, because nonmetals will eventually become negatively charged. And that will make us, once again, a new ionic compound. And that guy that comes out will have 0. So remember that for this reaction to take place, whatever that's coming in needs to be more reactive than what is replacing. And same thing up here. This guy needs to be more reactive. If it is less reactive, then the reaction will not take place. So for example here, if we look at our zinc, what is happening is the zinc is coming in and is kicking out the hydrogen. The hydrogen comes out as hydrogen gas, which I think we've done this a number of times. And that is the bubbles that you see, like in your test tube, and like you put your thumb over it, right? We light the little thing on fire to hear it bark, right? As you put it in there. And it makes zinc chloride. So this is a single replacement reaction. This is also still a redox reaction that's happening. If you look here, the zinc is 0. This is HCl. The hydrogen is +1. The chloride is -1 in this case. The hydrogen H2, that is naturally how it comes. And the zinc over here has a +2, and the chloride is -1 over here. So once again, if you kind of did your number line thing there to figure out what is going on, the zinc starts at 0 in this case and ends at +2, which means the zinc is moving in a positive direction. So in this case, it is the zinc that is getting oxidized. If we look at the hydrogen, actually, in this case, the hydrogen on the left-hand side is +1, which would be about here, right? And it ends at 0, basically. The hydrogen here is actually moving in the negative direction. And there's the hydrogen here that is getting reduced in this case. What about the chloride? Is anything happening to it? It's not. It's -1 on both sides. So it is actually a spectator ion. You could actually, if you wanted to, write a total ionic equation for this. This would be this plus this plus this. Again, it's going to break apart. Hydrogen, which is a gas, will stay together. And our zinc chloride will also break apart. Let me just get rid of some of my writing there. Here. So we would have zinc and 2 chlorides in this case. And this would be our total ionic equation. And the only thing that's a spectator ion in this case, as you can see, it looks exactly the same on both sides, is the chloride. It is our spectator ion. And that leaves us our net ionic equation of what is really happening here, which is this. And ultimately what is happening is the zinc is sending a couple of electrons over to the H plus, and the H plus gains those electrons, and now will become hydrogen gas, which is all those bubbles that you see in the test tube when you do this. And again, that is what you're igniting, obviously, when you put your thumb in that little wood splint in it. Yeah.
Clarify, you're saying that a simple replacement reaction can also be a redox reaction?
That's exactly what I'm saying. So it actually is a redox reaction. So you should think of like a redox reaction as like the big umbrella of classification. And underneath that redox classification, you can more specifically classify a reaction in other ways. Like more specifically, it is a redox reaction, but more specifically here, people would classify it perhaps as a single replacement reaction where this guy is coming in. Just like you should think of double displacement reactions as like the big umbrella of classification. And more specifically under that umbrella of classifications, you could have a precipitation reaction because you had a reaction that made a solid. And you could also have a acid-base neutralization reaction because somebody made water basically as a result of that. So we have kind of those two big classification reactions. And underneath them, we have these kind of more specific ways you could classify the same reaction. And you can classify the same reaction in multiple ways. As you can see here, this could be a single replacement reaction. It also could be classified as a redox reaction that's happening. No. So that's what we were talking about a second ago. If you look at any double displacement reaction, when you look at like the oxidation state or the charges of everybody on each side, they stay the same. So like before, I think I would have the barium on one side was +2 and the barium on the other side was +2. There's no changing of any of those charges. And because there's no change of the charges in that case, there's no electrons being transferred at that point. So it's not a redox reaction. Yeah. Other questions? Yeah. Yeah, it truly is it is sort of a covalent compound, but In this case, it's an acid, which means it's already in solution. And because it's really hydrochloric acid, it's going to be a strong acid and a strong electrolyte, which means at that point, when it's in that solution, it's going to actually be ions at that point. So it's going to be H plus and Cl minus floating around. Yeah, yeah, I would look at it definitely as an acid, especially when you see the aqueous next to it. Now, if it was a gas, you'd be right, it would be sort of covalently bonded and it wouldn't break apart actually in that case. But in the aqueous form, it actually does become like the acid, and then there are ions at that point. Other questions? Okay. Now, another type of reaction is a combustion reaction, and this also falls under the redox umbrella. So this is also a redox reaction. Now, I would say 99% of the time, if you are talking about in your everyday life a combustion reaction, I don't know why you're doing that, but in case you're having that conversation with somebody about a combustion reaction, most likely you're going to be talking about the organic combustion reaction. And that is when you take an organic compound that has basically carbons, hydrogens, and oxygens, like methane that comes out when you light your Bunsen burner. You would react it with O2, and you typically will always get CO2 and water unless you have an incomplete combustion, and then you actually get carbon monoxide, but usually it's CO2 and water. And I would say probably 9 times out of 10, maybe even more than that, that's probably, the combustion reaction that you will see. But truthfully speaking, you actually only need the presence of O2 for it to be a combustion reaction. So technically, if you see O2 being there, can be a combustion reaction, and that is what the one that we saw when we did it there in lab, which was this one. A little 2 there, a little 2 there. This is our don't look at it but observe it burn brightly magnesium oxide example when we burn it. This is a combustion reaction because it does have oxygen. It is also, as we talked about earlier, still a redox reaction, right? So 0, 0, plus 2, minus 2, so electrons being transferred. So it is a redox reaction. So I would say, again, 9 times out of 10, probably the organic combustion is what people would be looking at. But basically, that is all you really technically need for it to be a combustion reaction is O2 being present by itself there on the left-hand side of the arrow. Now, another classification of reactions, a more specific classification, is a synthesis or combination reaction. And in a synthesis or combination reaction, this is still under the umbrella of redox reactions. It is basically 2 things make 1 thing. So 2 things make 1 thing is your classic synthesis reaction or combination. So if you take H2 and O2, 2 things make 1 thing, make some water, a little sodium chlorine, make some sodium chloride. That is also 2 things make 1 thing. By the way, the one we just looked at a second ago, I would also perhaps argue is also 2 things that make 1 thing, right? So that is a synthesis reaction. We just talked about it being a combustion reaction, and it's also a redox reaction. So this particular reaction here, you technically could classify in 3 different ways. Which one you should choose? I would say probably the one that is what you're looking at. I would say most people probably would go either synthesis on this one or redox and maybe combustion as well. But probably synthesis is probably what most people would look at this one. 2 things make 1 thing. But it's a good illustration of you can look at the same reaction, actually classify it multiple ways depending on sort of what you are looking at. Any questions on that there? Now, the next classification is a decomposition reaction, and it is basically the opposite of what we've been talking about there with a synthesis. Synthesis, you put it together. Decomposition, you break it apart. So 1 thing makes multiple things here. Probably not surprising, this is also under the classification of a redox reaction. So here we have some water like we did in that experiment, put a 9-volt battery in there, break up the water into hydrogen gas and oxygen gas. This is actually one thing making two things. By the way, when we go backwards in this reaction, it is still a redox reaction, but things change because over here, that's +1 and -2 for the oxygen, 0 and 0. So when you're going in the backwards route, the hydrogen is starting at +1 and ending at 0. So it's the hydrogen that is getting reduced. The oxygen is starting at -2 and ending at 0. And it is the oxygen that is getting oxidized as you go in this direction. And that is different than what is happening when you put it together in a synthesis reaction. In a synthesis reaction, those got opposite things are happening because you're going from 0, 0 to +1, -2 in a synthesis reaction. And in this case, the hydrogen is actually going from 0 to +1. So the hydrogen is actually being oxidized and the oxygen is being reduced in this case. So obviously it makes sense. Putting it together is going in one direction, breaking it apart is going in the opposite direction. So they actually switch what's happening as you go in the opposite direction. Any questions on that there? Okay. So to finish up in terms of these classifications, again, there is the double displacement big category, which is our, again, two ionic compounds switching partners. And underneath there, more specifically, you could classify that as a precipitation reaction where a solid is formed. You could also have your acid-base neutralization reactions where water is formed. And remember, there is no transfer of electrons happening in either of these. Under the big classification of redox reactions where you get a transfer of electrons, you can more specifically classify that as a synthesis or combination reaction where two things make one thing. You could have a decomposition reaction where one thing breaks apart into multiple things. You could have a single replacement reaction where you have an ionic compound where one guy's coming in and kicking out the other guy. And again, by the way, how do we know that reaction is going to happen? One way that you can know this reaction is going to happen is sometimes you can look at what is known as an activity series. An activity series is just a list of a bunch of elements, and usually hydrogen somewhere in the middle. And anything higher in the list will replace anybody lower, so anybody higher will replace lower. Place there, lower on the list. So for example, you would have zinc higher than hydrogen, so that reaction with zinc will take place. Now, anything lower on the list will not replace. Anybody higher on the list. So for example, if you did that same one with copper, and you're trying to do copper in the HCl, it would not take place because copper is actually less reactive than hydrogen, so it will not take place. So again, the activity series is something that you could use if you come across it, and that's basically how you use it. Anybody higher will replace anybody lower will not. We actually did in that experiment we were talking about with the halogens, our ohm activity series, if you remember, and most of the nonmetals is our group 7, right, where we have fluorine, chlorine, bromine, and iodine. If you remember when we did that, the reactivity increased as you go up. So fluorine is more reactive than chlorine. Chlorine is more reactive than bromine. Bromine is more reactive than iodine. If you remember when we got to the iodine, it didn't replace anybody, right? So it stayed purple. And that means that if we try to do chlorine to replace bromine, it should work. But if you try to do bromine to replace chlorine, it will not work. So group 7 there is for the halogens, and that's the activity series basically for our halogens, it's just looking at group 7. Now, lastly here, also in a redox reaction is a combustion reaction. And again, all you really need for that is O2, but most organic combustions will produce CO2 and water if you're starting with an organic. Any questions on it? Yeah. Yeah, usually it needs to be only on the reactant side, and it has to be O2 by itself, and it's like gas form, natural form, molecular oxygen, basically. But definitely, if you see a reaction like the bottom one there, where you see O2 on the left and CO2 on the water, CO2 plus water, is definitely going to be a combustion reaction. So it's almost a no-brainer on that particular one there. Questions on that there? That wraps up chapter 7. We're going to kind of put together a couple of things that we've been talking about in some of these previous chapters, which is balancing equations and calculations like grams per mole. So remember that to go from grams to moles, or to go from moles to grams, it is the molar mass that is the most important conversion to do that. We get, again, the molar mass from the periodic table. It is the number that's on the bottom. So again, if we had something like water, we basically just add up all the parts. So we go to periodic table, and there are 2 times 1.008 grams per mole, which is basically the molar mass of hydrogen from the periodic table. We would go to periodic table, find our oxygen. We would add that, and that would be the molar mass there for oxygen. And we would add it together, and we would get something like 18.02 grams per mole. That is the molar mass of water. It is really used as a conversion factor to do like dimensional analysis. You could go 18.02 grams per mole. You could also flip it around. A mole is 18.02 grams. So we could do that for anything. We could always get that, and that is extremely important in these type of problems we're going to do in this chapter, which is based on stoichiometry. Molar mass going grams to moles or moles grams is used a lot. So, if we had like 32.5 grams of water and want to know how many moles of water that was, we would set it up dimensional analysis way. Usually when you calculate molar mass, it is the number always stays with the grams part, and it's always per 1 mole. And we would want to use, in this case, the conversion factor here on the right. That would give us 18.02 grams of water per mole of water. And that's going to get us there. And usually molar mass, we go about 4 significant figures. So 1.80 moles of water. So that is a really important conversion. Also, going backwards from moles back to grams, which obviously would be the opposite sort of calculation. If you had, say, 4.5 moles of CH4 and you want to know how many grams that was, again, you would go to the periodic table. You would find carbon, which is 12.01. You would find our hydrogen, which is 1.008. We could calculate the molar mass of CH4 by, again, just adding up the parts. So there's 1 carbon at 12.01 for the carbon. We would add it to 4 times 1.008 grams per mole, which is for our hydrogen. And that's going to get us there. 1604 grams per mole, which is our molar mass of CH4. And now we could actually do our calculation here. And again, I'm just going to kind of get rid of some of this. So I got somewhere to write, maybe up here. And what we would do is we would start with our 4.5 moles of CH4. Remember, opposites are going to cancel. So we do need to put the moles on the bottom. So we'll do the moles of CH4 And again, from the periodic table, 16.04 grams. The moles are going to cancel, and that would get us 72.18 grams of CH4. So those two conversions going from grams to moles, our moles back to grams, are used tremendously a lot in these calculations in this chapter where we do stoichiometry. It is also important to remember that a very common error that people make when they do molar mass is when they look, say, at an equation. Let's just say here. So they look at a balanced equation. Let's just say on one side they had 4 waters in the balanced equation, and they need to do the molar mass for a calculation. That 4 right there has absolutely nothing to do with molar mass. So whenever you calculate molar mass, it is only based off of the formula. So regardless if there's a 4 in front of water or a 42 in front of water, if you need the molar mass for water, it is still this number here, 18.02 grams per mole. That 4 in front is actually what we're going to use with our calculations in this chapter, and you do not want to use it with your molar mass. So whenever you need to use molar mass and you use a lot of, like I said, these calculations, you just take the formula by itself, one of the formulas by itself. Again, you add up all the parts, and that'll give you the proper molar mass. If you need to use the coefficient in front, you'll use it in a different part of the calculation, but you don't ever want to do it in both parts because you'll get the wrong answer. And that's really what molar mass is. It's how many grams there are per 1 mole of a substance, and 1 mole of a substance would be just the formula by itself, one of those, not 4 of them, for example, in this example here. Any questions on that there? Yeah. Yeah. It probably actually should be 2 if I was really paying attention, but it should actually be 2. Yeah. If that's what you're asking, it actually should be this right there. And this would be considered more of an exact number, so it should really be based off of that there. So, yeah.
The same standard.
Yeah, in this case, if you're calculating the molar mass, I would always at the end, it's just really common practice just to end up with 4 significant figures. So I wouldn't worry too much about, for example, if you're doing something like this, if that's what you're talking about down here, I wouldn't worry too much about the significant figure rules. What I would worry about is usually when you calculate molar mass, you should end up with 4 significant figures, and that's where I would round it to. That's just usually common practice. Most people aren't super strict on the rules, but if you are going to be really strict, then you would do the normal sig fig rules. But the general rule that pretty much most people kind of apply to molar mass is you usually end up with 4 significant figures. Yeah, I would say so. For sure. Yeah. Other questions? But up here, you should be a little bit more careful than I was, obviously. You should end up with 2 at the end there. All right. Well, hey, that was great seeing you for a day.